data. They've got all these sensors and all these tractors, and I don't know, like a big use case for a bunch of pretty exciting machine learning, and I don't know, it's a lot of fun.
It is.
Fun for me, kind of coming from like the ag background. It's like a nice way to use some domain knowledge.
That's cool.
You so are you at I guess Capitol Hill for
Yes.
Seattle U?
Yeah.
Okay, nice. You teach courses there too?
Yes, I teach physics and astronomy, sometimes data science.
Oh, cool.
Well, most of this is like data science.
Yeah, I'm always really curious about how they're using that. I don't know. I guess I've seen it for some like exoplanet detection and stuff like that, but I'm sure it's like way all over the place.
Yes, especially with the Rubin Observatory coming online fairly soon. There's
Oh, yeah.
so much data. There's no way a human could ever scan it. So the algorithms and the machine learning have to be pretty on point to trigger backup observations. So it's like a supernova goes off. It spots it. It triggers a warning to everybody around, like, look at this object right now.
Yeah.
So if anything's interesting, it triggers stuff.
Is there Rubin? Is that like
That's what the LFST started off being called.
okay, okay.
Large synoptic survey telescope.
Okay, okay, yeah. Yeah. You I know you teach that you like do broader stuff or really specialized courses? Okay.
So I teach the majors, I teach the general science majors and engineers, and we teach course classes. So what's the equivalent of astronomy 101? So
Okay.
all astronomers do that.
Yeah.
It's like almost like public service, and everybody likes it. Astronomy's gateway drug in science.
Yeah, that's got to be pretty fun, I guess. That's cool. And you did your PhD in London, right?
Yeah, Mary.
Cool.
So there are lots of colleges around London, like Imperial and King's College and Queen Mary. And when people ask me what's the college like compared to the US, like UW is a research one, an R1. Imperial, Queen Mary, King's College, they're all equivalent to R1s because they have a lot of grant money and they grant PhDs. So it's like the Ivy League equivalent are the really old universities like Oxford and Cambridge, which are also R1s.
Right.
But you know, they were what, 12th century, something like that.
Yeah, that's like okay, right?
Hey everyone, wanted to get started. It's 7 o'clock. Make sure we have enough time for our really great speaker, Dr. Hughes. So Alan, our president, couldn't be here today. He sends his regrets, but I will fill in for him for his state of the club, Seattle Astronomical Society. What's going on with our club as of this month? So did everybody get to see the lunar eclipse a few days ago? Yeah. I managed to sneak a quick picture using the telescope that Dave gave me, the little star blast. Worked really well and got a quick picture through the clouds. And, not as good as these, but these are some numbers. We had our speaker last time who was had her poem on the Blue Ghost lunar lander, and this is the picture of the eclipse from the moon that the lander took a big eclipse. So little diamond ring effect there. Here, what the lunar eclipse looked like from the moon. So yeah, welcome everyone. And just to update you really quickly on some upcoming events we
I
have
did not understand what I was looking at there.
with the lunar eclipse.
Yeah, the Earth is 4 times the diameter of of the moon, and it looks to me like I was seeing a diamond ring and a pulsing body that's the same size, actual size as the sun.
So yeah, my understanding is that the atmosphere can refract some light from the sun around the bulk of the Earth.
I just didn't think I was looking at an occulting body that was 4 times wider than the sun.
In terms of like why it was red.
No. What's it seen from the moon?
Oh, that one, okay.
Okay, so I think yeah.
The ratios are the same whether you're looking at the Earth or whether you're looking from the moon. They're the same ratio.
So the Earth looks the same size as the sun from the moon?
That sounds completely wrong.
I'm not sure. I do think that the atmosphere allows some of the light to get around the limb of the Earth, where you wouldn't have that effect, I think, with the if the Earth had no atmosphere.
That's kind of probably right. That's probably what's wrong.
Yeah. Which is why my favorite thing about lunar eclipses is that the moon is red because you're looking at the simultaneous sunrises and sunsets everywhere on the Earth at the same time.
Yes.
Projected onto the moon. That was kind of cool. Okay, so anyway, so upcoming events, we do have some start parties this weekend. Hopefully the clouds will break. We'll see. We have our Paramount Park start party up close to the shoreline. We also have our women's special interest group book discussion on that Saturday as well. We have a Tiny Woods, our dark sky site down here near Goldendale. We have a Messier marathon for members next weekend. So we'll talk about that in a moment. And that also weekend we have here up north, we have in Duval, our star party, our Covington star party, and also Steve Case, who runs that star party, also gives a beginner astronomy class down in Covington. So new members, that might be a good opportunity for you guys to learn a little bit about how to navigate the night sky. And if you can't make that one, then we have Keith here, who does another similar star party, similar astronomy class in Woodinville. So if you don't go all the way down to Covington and you're up north, that's a sort of a similar class for anyone, but especially for newer members and people that want an intro to the night sky in Woodinville. So look for those on the calendar. Too. This is the same star party again in Covington. I'm thinking Alan might have left that in as a typo. I don't think we have the same star party 2 weekends in a row, but I could be wrong. I think that might be a typo. And then yeah, on April 8th, Tuesday, we have our special interest group for astrophotography. That's a Zoom meeting open to the public. A lot of really interesting talk about our members that are into astrophotography and what their latest experiences have been. And then lastly, we have the next day, we have our next SAS board meeting. Just as a reminder, that's on Zoom. It's also in person at the Museum of Light. And it's open to the public. Anyone, you don't even have to be a member to come. So we welcome anyone that wants to attend, either remotely or in person, to come to our board meetings. Okay. So yeah, just to speak of the Messier Marathon, the Messier list of 110 objects compiled by Charles Messier back in the 18th century he was in France, but Seattle happens to be a pretty similar latitude to France, so it's actually a pretty good list for Seattle as well. And in late March, you can see all of them in one night if you know where to look. And we're going to have a Messier marathon. That's what people doing Messier marathon. You can try to see all 110 objects in one night. We are going to try to do that at our dark sky site in Tiny Woods. This is a new dark sky site just this year for this club. And I haven't been down there yet, but I'm trying to get down there the end of this month, at least this summer. Because I've heard it's really, really great skies. And we have a lot of nice facilities going up there. So if you guys are interested in going to that Messier marathon, if you're a member, I would highly recommend it. It's a lot of members that are looking. Even if you don't know exactly where to find things, a lot of people will be there to help you and kind of point you in the right direction. And even if you don't find all 110, it's still gonna be a lot of fun. So I would recommend looking into that, and you can send your log, you can keep track of which Messier objects that you find. You can log them and send that log to mm@clastro.org. even if you don't go to the dark sky site, you can do your own SA marathon. And we will send you a certificate commemorating your achievements. So keep that in mind. We are going to have some new signage for start parties. They actually have one serving for a signage for this event right there. But these are our new signs for the start parties, and they'll have a code for your phone to direct you to the website and telling you who the host is for that particular start party. So look for those at the next SAS start party that you go to. Also coming up is this UW lecture series for some really great astronomers, very similar to our talk tonight. Lots of different great topics from scientists from around the country. They're all coming to UW over the course of April. You do have to register for that event, but it is free and open to the public, so highly recommend that. We have some SAS hoodies and polos available. I need to get one of those for myself, come to think of it, but at Cloud Break Optics. So yeah, if you want some SAS swag, feel free. And then yeah, so I'm gonna shut up because I really want to hear this talk. Dr. Joanne Hughes, Associate Professor of Physics at Seattle University, and Affiliate Professor of Astronomy at UW, and she's going to talk to us about globular clusters and titled Destruction of Globular Clusters. So I will let Dr. Hughes take it away.
Hello, nice to see everybody, and if you can't place my accent, I'm Welsh. So I've lived here for half my life. I lived in London for about 7 years too, so hopefully everybody's familiar with the BBC and I won't talk too fast. Okay, so this talk can either take 30 minutes or an hour, depending on how much you want to talk. So this image is essentially the Gaia catalog. So every one of these points is a star. It's over 2 billion stars, not just in our galaxy, but also the Large and the Small Magellanic Clouds and other galaxies in there, if they're above G20th magnitude. What I'm going to be talking about tonight is the project that myself and my research students have been doing on the globular clusters in the bulge of the galaxy. Now, star clusters, yeah, I was an amateur astronomer too. I had a sea star, so I'm always taking photos. I work on Capitol Hill. We have 11-inch celestial on the roof, but it stares straight at Swedish. I live on the Kitsap Peninsula, so I take our sea star home and take lovely images. But my professional telescopes are usually over 3 meters, so I'll show you a few pictures of that as well. The usual suspects that we take images of as amateurs are usually open clusters and globular clusters. Omega Centauri is better seen from the south. Actually, most of the globular clusters are better seen from the south, except for the few outer halo ones like M92. But whenever you're trying to do something with galactic archaeology, most of the time you're using the globular clusters. So whenever I talk to school children, I usually have this snow globe, which basically has a spiral galaxy in it and some snow. And you can think of the halo stars and the globular clusters being the snow. So we're about the way out in this, looking towards the galactic center, which we can never see because of the dust lanes. But if you look out, you can see the halo globular clusters, but less well studied are the bulge globular clusters. So people who've done, should I wait that? people who've done any kind of study in astronomy know that the population one stars are the sun-like disk stars, relatively metal rich. Open clusters form part of this population, and it really tells you about the evolution of the disk. And if you're looking for extrasolar planets, that's the best place for you to look. But the population two stars are the old metal core halo bulge stars. This is where you can do galactic archaeology. Now, our universe is about 13.8 billion years old. The galaxy has been around for a few hundred million years less than the universe, but the globular clusters in our galaxy are all between 10 and 13.5 billion years old. So that tells us about the very early evolutionary stages of our galaxy. So as far as we know now, the Milky Way is about 250, 270 globular clusters. You keep finding more of them when you look through the very highly extincted, dusty parts of the galaxy. But you can use them to tell us about galaxy formation because they're very old. You don't have the conditions to make globular clusters anymore. But if you look at this diagram with the halo population going in cometry-like orbits, the disk population going in Keplerian solar system type orbits, I won't worry about the dark matter for a minute, and the bulge, we've got a peanut-shaped bulge, and anything orbiting in the bulge kind of goes in an X-shaped orbit. So the halo is mostly pretty old. The disk is mostly under 7 billion years old. And the bulge is a mixture of both populations. So we think that the bulge went pretty early. So this image comes from one of the NASA sites. So for the last about 25 years or so since the Sloan Digital Sky Survey, we've been able to discover lots of tidally stripped galaxies falling into the Milky Way and leaving streams behind them, like the Sagittarius stream and the Magellanic stream. And many of the haloglobular clusters also have streams behind them. But inside of the bar and the peanut, we don't have very good information, both of the globular cluster population and any tidal effects, that it should be pretty obvious gravitationally if you're looking at the population in the bulge where you've got trapped globular clusters, they should be tidally shredded by the gravitational field of the galaxy. Does that make sense? Cool. So this is the project that myself and my co-workers have been working on. So this is the Blanco Deccan bulge survey. And they took images over a long period of time of this bulge region, which contains over 250 million stars, lots of dust, and probably about 25 globular clusters, all in this fairly small area of the bulge. But that enables us to do a population census here. So what we've been doing is looking at the evolution of the bulge, picking at least 20 of these poorly studied globular clusters, using Gaia mostly to determine size, age, metallicity, chemical composition, and the membership, and then searching for tidal debris and trying to figure out how much of the bulge population has actually been stripped off these globular clusters.
So, sorry, would you like to have questions? Yeah, so the globular clusters are in the bulge, or are you seeing them through the bulge?
These are trapped in the bulge.
In the bulge, okay.
So we've been mapping their orbits. Some of them are in halo orbits, and once in a while you'll find them move down. But the globular clusters that we're looking at are mostly bulge globular.
So the tidal stars, can you explain that again? That's what you're talking about. They full.
So,
I understand the strings and all that, but I don't understand what an extra tidal star is.
okay. I will come back to this. There. So, gravitationally, the most famous one in the halo is Palomar 5, and it's been known to have tidal streams associated with it visually for that long period of time. And so if you do a calculation of what's gravitationally bound to the globular cluster and what's unbound and bound to the galaxy, those are what the extratidal stars are. So we'll yes. Yeah, it's like spaghetti.
Could they also be stars from the Milky Way that are being gravitationally pulled towards the cluster?
That's what we're trying to figure out.
Okay.
So we started this about 3 or 4 years ago. So I'm working with Andrew Thunder, who's at St. Martin's University, and Katie Devine at College of Idaho, and Kevin Cody and a few other people at Western Washington. So we started off by doing a test project from this survey data, Gaia and BBS, and we got follow-up spectroscopy to figure out the real motions and the chemical composition of these stars. So we took these test fields at the Anglo-Australian Telescope, which is 3.9 meters at Mount Stromlo and Siding Springs, and we got a Kickstarter grant from LSST to start doing this. So our original data, you can see most of the astronomy happens in nice warm control rooms. And we continued this. So this is spring of 2023. That's me and Andrea. And we were at Apache Point Observatory, which is a 3.5 meter telescope you control remotely once you've been checked out on it. And this is us being checked out on it. And so this is also Apollo, which is firing a laser at the moon, because the Apollo astronauts left a reflector there. And the new lander, which might be on its side, can still be hit with a laser anyway. It still works. So, oh, I just wanted to show you this. This was our collaborations taking some images. The 3.5 meter at Apache Point is one of the few telescopes you can put an eyepiece on. And so we all got to look for several hours. And then I used my iPhone, and I got, this is the eyepiece of my iPhone, which is a lot better than my C-star photo, because this is a 3.5 meter telescope. And it's lovely in the Sacramento Mountains. And we were playing around also with the images, because 2 days before this run, a supernova went off in N101. So we got to take some data for the project, which was a lot of fun. So this was our last group meeting. So we all went up to LIGO, had a private tour of LIGO, which is fun. If anybody doesn't know what that is, that's the gravitational wave observatory. And this is one of my research students at Seattle U, Fiona. Fiona won a prize at the MJ Murdoch Undergraduate Research Conference in November, giving a talk about our research, and she's off to Paris to do optics this summer on a research experience. Go here.
Wow.
So before Gaia, you had to figure out a period luminosity relationship for the variable stars, usually the RR Leo stars, for the globular clusters to figure out their distances. But with Gaia, you've mostly got that data now, but you can test what's going on there. I always say when I give this talk to my own college where there's a big chemistry department, please don't hate me, that astronomers have a tendency to call the hydrogen content X, the helium content Y, and everything else that isn't hydrogen and helium Z, the metallicity. I'm sorry. So the UW professor I worked for, George Wallerstein, I'm pretty sure he invented this notation. So Fe over H is a way of getting the metallicity.
Just 1 second, I'm so sorry.
Hi everyone, apparently there's a Subaru parked on the right side of the road here on Leary that is parked in front of the tow truck's lot. Not sure who it is, but they're saying if it's not moved, they will tow. So I just wanted to find out if there's somebody here.
It's more important.
Can't get out.
So Fe over H. This is the log abundance of iron relative to the sun. So solar metallicity is 0 on this scale. 10 times less is -1, 100 times less is -2. The most metal poor globular cluster is N92, which is about -2.6. So it's very, very metal poor. And the disk of the galaxy is about solar metallicity or up a bit. The globular clusters, as you can see from the diagram, are mostly low metallicity, but there are some weird ones. So it turns out that about 20 or 30 of the globular clusters weren't formed in the Milky Way. They were formed in dwarf galaxies and accreted from the other galaxies, even though the galaxy itself may have come apart. So M54 is the nuclear star cluster of the Sagittarius dwarf galaxy. Omega Centauri, the most massive globular cluster there is the nuclear star cluster of a shredded dwarf elliptical. So some of the most massive globular clusters aren't actually globular clusters. They're actually the nuclear star clusters of dwarf galaxies, which is interesting. So this is why I was talking about the metallicity. So I've color-coded it. So this is, I'm not sure if I press this. There you go. So in general, if it hasn't been accreted, the more metal-rich globular clusters are in the central regions of the galaxy. So that's the bulge globular clusters that we're interested in. So this is an interesting problem because the bulge was formed about 10 billion years ago. So some of these clusters have been trapped in the bulge for billions of years, losing their outer layers of stars to the general population. Yeah.
And what's causing that? Our old
Gravity. Just gravity. Yeah, the Milky Way is about 10 to the 11 solar masses, and globular clusters vary between a few thousand to about a few million solar masses, so the galaxy wins. So, getting back to Power 5, so we've known about these tidal tails for 25 years or so, that Power 5 is on a long elliptical halo orbit, and so its tidal debris is just really obvious. But basically, you can't always pick out the tidal debris from even the halo globular clusters because they're at different points in their orbits. So this was something like Power 5, and the rest frame of the galaxy is on the left, and the rest frame of the cluster is on the right. And you can see that gravity is just causing tidal stretching, spaghettification, right? So you've got a leading tail and lagging tail. Near the globular cluster, it's kind of S-shaped, but then it strings the stars out around the orbit. But this is for the halo, so the halo is very simple.
What percentage of the mass of the globular cluster is put into these tails?
That's the big question. That's what you need n-body simulations for, to figure out whether it's 10% or 90% of these globular clusters. You know, the ones that we see now have survived for at least 10 million years. There are ones in the bulge that are 10 billion years old, and they've been trapped in the bulge for several billion years, but you've got to try and figure out how much of the population they've lost. Could be as much as 80 or 90%. So this is Gaia. Gaia just ran out of fuel. Its thrusters and was shut down. This is the best thing that happened to observational astronomy in decades, but probably since the Hubble Space Telescope, because this gives you positions, parallaxes, proper motions, photometry, which is imaging and measuring it. And if they're bright enough, you can also get spectra and radial velocities. Radial velocity is the velocity that shows up if you've got a component of motion straight towards you or away from you, not directly across your line of sight. So, I'm not sure if I can play this.
Yeah.
So this is what Gaia actually is. So it's the motion of the Earth around the sun, the motion of the sun around the galaxy, and then the motions of the stars everywhere else. If you have a globular cluster that's like tens of thousands of light years away, they're going to move together. So anything that's in the cluster, whether it's an ocean cluster or a globular cluster, you're going to see the stars move together. They're going to have similar proper motions, and they're also going to have similar radial velocities. And if they're all born at the same time in the same place, similar chemical compositions. Okay, so go to the next slide. Okay, so photometry. So we've all taken pretty pictures, and I've shown you some of my pretty pictures. And when you do photometry, you basically count, you know, how many electrons compared to how many photons in a certain annulus. I've got an aperture, and then you have a sky annulus, and you compare it to something that's a standard. And the brighter stars end up with bigger images, so you can do photometry from images. CCDs rather than photographic plates because you're not developing them in space. So spectroscopy works like a prism. So light comes in from your target, gets dispersed because different wavelengths of light get bent from different angles, rainbow effect. And you can measure the chemical composition of a star by the absorption lines in the upper atmosphere, which have a chemical fingerprint. And that's the Anglo-Australian telescope, which is 3.9 meters, and the AA Omega spectrograph, which has a fiber positioner, so you can take hundreds of spectra at one time. Saves time.
Doesn't that just tell you about the composition of the upper atmosphere? Like, could it be?
It does, but it's going to be the upper atmosphere of the star when it was born, because red giants mostly, they have a dredger, but the iron content is the iron content at birth, because those stars aren't usually in globular clusters massive enough to actually make iron. So they can make CNO and a few side processes, but they don't make iron. So the iron content is characteristic. So this is basically where you have all of these 22 odd globular clusters and their tidal debris, where a theoretical model like Gala, and I showed you the globular cluster coming apart. So we ran this for all of those clusters, and this is where we think the tidal debris ought to be. And so we took images a couple of years ago in the 3 heavy circles, and we're planning observations around here for this summer or next summer. And we've got some NSF money, should they give it to us, to go there. So the way you identify the cluster members before you take the spectra is you get the Gaia proper motions, and hopefully the cluster is separate from the field around them, and then you can figure out if the stars are moving together, are their proper motions the same from Gaia, are their radial velocities the same, mostly going to come from separate spectra. But unless the globular cluster is very close to us, you're not going to get spectra for Gaia. They're too faint. The bulge is too far away. The nearest bulge stars are probably almost 6,000 parsecs away.
How long do you have to wait before you can see proper motion of a star from that far away?
A couple of years, because Gaia's got the atmosphere.
Right.
So you identify a cluster, you get its proper motion, you get its radial velocity, and if you just have images, you use Bayesian statistics and machine learning to pick out the stars. So if you actually want to know how to do this, this is out on GitHub, and you can just pull the software down if you want it. So we did this first of all. So it turns out one of our favorite globular clusters, NGC 6569, it was one of our favorites because it's really bright. And the bulge is a really messy field, lots and lots of stars, lots of dust, and this one looks like a nice cluster. However, its proper motion is not very different from the field. Now, I may suggest that the reason why it's not very different from the field is maybe all the field stars came off this cluster, possibility. But it's not very easy to get the cluster and the field separated. So this was the color magnitude diagram. So I will show this to my students because this is Omega Centauri with the Hubble Space Telescope taken with 3 different filters, where the red filter is infrared, the green filter is actually corresponding to really blue, and the blue filter is just ultraviolet. So you sort them left to right. So temperature goes hot stars, cold stars, and you sort them by brightness. And that's a beautiful color magnitude diagram using 3 filters. And this is Omega Centauri that doesn't have a sharp turn off because it's not actually a globular cluster. So this is just, the center of the galaxy is in Sagittarius. The bulge is best seen from the southern hemisphere, but you can still see part of it. So this is a Hubble Space Telescope image. So this is just a whole bunch of stars in the center of Omega Centauri. Okay, we'll go to the next one. So that's the color magnitude diagram of NGC 6569, which looks like my bad, which was those stars in here with the spectra. So we picked over 300 fibers and looked for the tidal wave group. And so these are the spectra. This is just in the infrared, it's the calcium triplet. So you can see those 3 deep lines. That's calcium 2. And even if you have a really faint star, you can pick out the calcium triplet. So you can see the radial velocity shift from these lines, and you can get the chemical composition.
Does that mean it's red shifted or blue shifted relative to?
This one's blue shifted.
Blue shift, okay.
So the center of the globular cluster is about at minus 50 kilometers per second. And so when we've looked at previous studies, it goes from about minus 30 to about minus 63 kilometers per second because it's spreading out a bit.
Oh, that's not just our motion, that's the motion of this.
We've already taken our motion away.
Okay.
So there's, everything's moving. So the Earth is turning, the Earth is orbiting the sun. The barycenter of the solar system is orbiting the center of the galaxy. I take all of that out. And then you have the rest frame of barycenter. So this is the rest frame. And then you compare the shift of the lines to the lab. So it turns out that only the bright green stars actually belong to the globular cluster. And it turns out only 58 out of 303 spectra have the right radial velocities. And then we looked at them, compared the chemical compositions, or for you with that mean, but it turns out that there were 39 stars which were part of the tidal tails, and we had a whole bunch of other stars which weren't part of our tidal tails, but could have been part of other globular clusters nearby, other tidal tails. So this is the orbit of 6569, and this is how the stars should be tidally stripped. So we're here, the center of the galaxy is here, and the peanut-shaped bulge, over a couple of 100 million years, this globular cluster will orbit all the way around the bulge, leaving stars behind it. So, without getting into too much detail, so this is the center of the cluster. This is the radius of the cluster. This is the tidal radius of the cluster. So anything within the tidal radius belongs to the globular cluster. Anything outside it belongs to the galaxy and doesn't go back in. So it turns out we found the tidal tails, and we found them just barely visually, but we found them with spectroscopy. And so this was a very massive globular cluster, but it was not well separated from the field, that it looks like it's been losing its stars in this way for billions of years. So quite a large proportion, maybe 50 to 80% of its stars, have come off already and are part of the general bulge population. So we're going to get more data on this. So this is basically, there are two core magnitude diagrams here. One is of the cluster and its tidal debris, and there's also a little bit on the front of the bulge, which is in our line of sight. Because a few of them are actually having the same orbital properties, and we pick them up again. And we always wondered why it had a double horizontal branch. The horizontal branch is here. It's because we're looking at stars that have come off the star cluster in our line of sight. And enough of them are moving the same way. So we are going to go through and look at a lot of the tidal debris and model it with what we call n-body simulations and find the rest of the tidal debris. We didn't think we'd find it because the bulge is so messy. And this was another one that we're working on, 6544. This one's on the front side of the bulge. So stars are a lot brighter. So I had my student Fiona look at this one, and this one is really well separated from the bulge population, like way off in proper motion. But you can see it's not spherical, right? That's what the tidal debris is doing. It's pulling stars off, but it's not doing it uniformly. It's stretching it in one direction and pulling the stars off in the other direction. So we've got its core magnitude diagram. You don't need that. But this is the data. So this is its orbit, and this is where all the stars are coming off it. And so this is what you have. Here's the center. Here's 1 through 5 tidal radii, and here are the tidal tails making the globular cluster non-spherical. So as we're going on, people are working on simulations of the whole universe and Milky Way-like galaxies. And we're seeing this kind of behavior, but now we can really tell what population of the bulge globular clusters are donating to the rest of the population. So this is the very ancient population 13 to 10 billion years ago, because none of these globular clusters are any younger than that. So the bulge actually formed really early, which was not something that we were really sure about. So we're working on this. My students, I've always had between 2 and 7 undergraduate students. Some of them are physics majors, but I've also got mechanical engineers and computer science people working with me, because we need all of this kind of expertise. Also optical engineers to build the telescopes. So hopefully you found that a little bit interesting. I'm here to answer any questions that you have. But come and visit us at Seattle sometime. It's fun. So it's getting a little bigger over time, but it's also, we're a barred spiral galaxy, but we've got this boxy bulge. So some of the interactions with the other dwarf galaxies falling in are actually maintaining this shape. So it seems to be that the bulge, unless you have a major merger, when Andromeda actually runs into us in a couple of million years, it's actually maintained its shape for a long period of time. But we've also got to try and model how long these globular clusters have been stuck in the bulge orbits, because they should have been shedding stars all that time. So our galaxy has a younger population in the disk, which is actively forming stars. It has a mixed population in the bulge, very old stars and some younger stars, and there's no active star formation in the halo. And our galaxy doesn't have the conditions to make globular clusters now, because they need to form really fast and have a lot of gas available. Yeah. Although it'll probably happen when we merge with Andromeda, because those disks will provide enough gas to do it. And will eventually use up all the interstellar medium and merge the black holes and, you know, destroy the spiral galaxies that end up as an elliptical galaxy. Fun.
When the globular clusters kind of are getting stretched out or perturbed, or when they're sort of crashing through the bulge, does that set off any star formation just from perturbing all the gas and dust and other stars?
When they fall in, they can cause some shocks, but the disk also shocks the globular clusters and also causes mass loss. So when you look at the theoretical models, any kind of interaction can set off a shock wave from stars, but the disk is massive. So if a star cluster falls through a dense part of the disk, it's going to come off worse.
How can we separate the rest of the ball? And we presented some criteria.
Yeah.
So like experimentally, how much do you get?
Depends on the globular cluster. So 65, 69, the one I suspect had actually been donating a large amount of field stars to the general population, has probably been there for billions of years doing that. So we're trying to figure out what percentage of the bulge field stars came off the globular clusters. But we need to do more than just 2 or 3 globular clusters to figure that out. But the models seem to indicate that there could be a significant amount of the older population has come off these star clusters. And some of these star clusters, if they were smaller than this one, will have come apart entirely and probably followed those weird boxy shaped orbits. Yeah.
Do the stars and globular clusters like tend to come from the same nebula and form at the same time? Like do they just gravitationally attract each other? No. What's that work?
They're mostly formed out of the same cloud of gas in the early universe, which has mostly the same chemical composition within a few tens to a few hundred millions of years. So the first, if stars are born with a range of masses, they do seem to be. The massive stars don't live very long. But when they go supernova, the chemical composition is such that it kind of blows out some of the material out of the gas cloud. So most of the globular clusters don't have a range in ion content. So things like omega-10 and N22 do have a range in ion content, which means they were bigger, they collected more gas, and star formation could have happened for longer. But most of the globular clusters have mostly the same chemical composition and are roughly the same age population as well. They have a bit of a light element variation, but nobody's exactly sure why, whether it was asymptotic giant branch stars dumping material onto the still forming stars. That could have been one reason. Or rapidly rotating massive stars could have dumped some processed material there too. So they have a little bit of a variation in certain elements, but not usually iron content.
I think I'm remembering this correctly, that there are other galaxies that we can see that have many more globular clusters than the Milky Way does, like maybe even thousands. Do we know
Yes.
why that's the case?
I can't remember which giant elliptical galaxy, like a CD galaxy, had 16,000. But those are usually the centers of dense galaxy clusters, so they've cannibalized a lot of other galaxies. And during that process, you could form a lot of globular clusters, not just take them from other galaxies, but have the conditions to form a lot of them. So I could probably send you the image that I remember from HST, that it looks like there's a giant elliptical galaxy. It looks like there are a lot of stars on the outside, but all of them are globular clusters, each containing, up to 1 million stars themselves. But it just needs very extreme conditions in the gas to make it. But isn't it beautiful? I love taking images of globular clusters. Some of my favorite objects. Any other questions?
So what's the next step for you? Where are you headed, down the road here?
So we've got the time booked for the Anglo-Australian telescope to do more of these fields. And we're also working with the computer science department, getting some students just working on n-body simulations to try and figure out what's going on in the bulge. And I'm just about to submit the fourth paper on this and trying to get publications for all my undergraduate students. But in small colleges, you quite often have a lot of undergraduate research going on because you don't have grad students, you don't have postdocs, but it's also a great way to teach people how to be scientists, even if they're not going to be astronomers. It's giving them publications and teaching them the scientific method. Okay.
The AI thing I started to play a little bit of for you.
Yeah.
They started looking at dark matter. Was there anything coming up for you in that region?
Well, the globular clusters and their orbits do trace the potential of the galaxy. So that gets at it some way. However, I've been the last couple of years reviewing some proposals, and axions are a type of subatomic particle that has been popularized by some theorists lately, and since the weakly interacting massive particles have fallen out of favor a bit, they're going axion hunting right now. But as an observer, and if I'm modeling it, I'm trying not to be biased as to what I think dark matter is. And if it doesn't exist, we've got gravity really gone. but we keep on not breaking general relativity. So that can't be it. It has to be something in the weak field case. But you can't have the modified Newtonian dynamics and some of the observations that indicate dark matter. So it's still an open question. And who knows what the funding situation is going to be. But they've not found the dark matter particle in the particle accelerators. And the most promising candidates, theoretically, they should have been found by now. Okay, thank you very much.
Okay, so thanks everybody for coming. That was a really amazing talk. Thank you so much, Dr. Hughes, for coming out to tell us about your work. And didn't have anything else planned for tonight, but if everyone wants to hang around and talk and enjoy ourselves, have beer, or have a hot dog, feel free. And otherwise, have a good night.
Thank you.
One of the guys you have working meeting? Okay, that's great. Kind of eliminating.